Hello. Firstly, I'd like to thank the organisers for hosting this hybrid conference and giving me the opportunity to talk about artwork. My name is Nick Hu. I'm a PhD student at the University of Oxford under the supervision of Jamie Vickery, with whom this is joint work. I'll be talking about trace monoidal categories as a kind of categorified algebra, and 10 minutes is really a short time, so instead of trying to go into all the details, I'll just give the broad brushstrokes of what we did so that you guys can try and get a flavour. I should also mention that this work was accepted at MFPS, so if you are interested, please check out the accompanying paper there, or tune into that conference which is happening at the same time as CT, and you can hear me give a 20-minute version of this talk. So without further ado, let's get started. So what do I mean by tracing? The notion of tracing is a very natural one, and it captures what we might mean by recursion or feedback. In mathematics, we make use of induction all the time, and this is intimately related to recursion. That is, we make use of inductive proof principles to prove things about recursively defined structures, for instance, the natural numbers, and the corresponding induction principle. In computer programming, recursion is heavily used as an abstraction tool because a large problem can often be solved by breaking it up into smaller recursive subproblems. A simple example of this is the factorial function. So to find the factorial of some natural number n, it's sufficient to recursively find the factorial of n minus 1 and multiply it to n, which is what this line here denotes. Recursion appears not only in code, but in data too. Many Wikipedia pages have a side panel image illustrating what the page is about, and you can see here the article corresponding to the Wikipedia page for web page, which recursively contains a screenshot of itself. And over here on the left, we have a depiction of the ancient mythological serpent Ouroboros, which is eating its own tail. And in particular, I want to draw your attention to the way that this serpent is depicted. It's drawn as a circle feeding back into itself. This is a category theory conference, so I need to talk about category theory. And category theory formalizes this notion as a trace monoidal category. This is originally defined by Joyal, Street, and Verity. A trace monoidal category is a structure on a monoidal category which nicely sends each morphism sharing a component in its domain and codomain to its trace. In the category of finite dimensional vector spaces, this generalizes the standard notion of trace from linear algebra in some appropriate sense. Rather than writing out each niceness axiom as an equation on this slide, I would prefer to move to the diagrammatic calculus of monoidal categories. For those who haven't seen string diagrams before, they can be seen as the Poincare dual of pasting diagrams. Objects are represented by edges and morphisms are represented by nodes. Ordinary composition goes up the page and tensorial composition is horizontal left to right. So for example, we would draw the tensor product of A and B with two vertical wires next to each other labeled A and B respectively. Graphically, we represent the action of sending a morphism to its trace as joining the traced out legs into a loop, just like Ouroboros. Now, there are certain niceness conditions that I mentioned before that the operation has to satisfy. The tightening axiom says that tracing this composite of H, F, and G is the same thing as just tracing the F part and then composing it with H and G like so. The sliding axiom says that either composite of F and G is the same under tracing. Yanking, which only applies when our category is symmetric monoidal, says that tracing out the braid is the identity morphism. But what I've drawn here is a slight generalization in which we have a balanced monoidal category, in which case tracing the braid gives the twist. Moreover, there are two vanishing axioms. The first one says that tracing along the unit of the monoid is the same thing as applying the uniters. And the second one says that when it's possible to trace out some tensor products, x tensor y, then tracing each component in sequence is the same thing as tracing out the entire thing in one step. Finally, there's a superposing axiom which states that G tensor, the trace of F, is the same thing as the trace of G tensor F. So roughly, the axioms for trace monoidal categories can be partitioned into two types. The structural ones, here in yellow, and compatibility with a tensor, here in green. Now we seek to study these structures abstractly, and just how one category theory provides an arena to study standard mathematical objects like sets, groups, vector spaces, etc., we can use the theory of bicategories to study one categories. The natural place in which to look is CAT, the two categories of categories, functors, and natural transformations. However, CAT has a major flaw, namely the lack of a Yoneda principle. The next best thing is Prof, the bicategory of profunctors. This bicategory has lots of different names. I've seen distributors, bimodules, relators. I'm sure it's got many more names. And this bicategory has lots of different uses. But a useful intuition for me is that a profunctor is like a categorified relation, just like how a functor is a categorified function. So for instance, if you have a relation between two sets, then for every element of the Cartesian product, it tells you whether or not they're related. Analogously, in this situation, where you have a profunctor C to D, it tells you whether an object of D up times C, for instance, X and Y, it will give you a set. And this set is like a truth value telling you how X and Y are related. The prototypical example of a profunctor is a Hom functor. So suppose you have an endoprofunctor on C. That's precisely given by the data of a functor C up times C to set. And the natural choice for this is the Hom functor. These are pretty important profunctors. They give the identity profunctors, and also they generate all of the compact structure of Prof as a compact closed bicategory. In some sense, moving from cat to Prof is akin to moving from set to rel, and lots of intuitions we would like to use also hold there. For instance, every function is a relation, and a fancy way of saying that is set embeds into rel. And in some appropriate sense, every functor is a profunctor, which is justified by the embedding of cat into Prof. Moreover, just like rel, Prof is compact closed, so it admits a rich diagrammatic calculus with symmetry in cups and caps. So this is the appropriate setting in which we can find a categorical algebra which faithfully represents trace monoidal categories. And importantly, the ambient language is rich and structured, so we can easily state what we want to prove and produce the proofs concisely and diagrammatically. What do I mean by categorical algebra? Consider the very basic definition of a monoid, a carrier set equipped with some associative unital binary operation. We can capture the essence of this structure as algebraic data, a single object equipped with some with some morphisms and some equations, and we call this the externalization of the monoid. This can now be interpreted in any monoidal category, and when you interpret it in the monoidal category set, you recover the original internal definition. And in other contexts, you get other interesting structures. So this is the kind of thing we want to do to the structure of trace monoidal category. So here's how we do it. We call a traced pseudomonoid a pseudomonoid equipped with this additional two morphism on the left, subject to these three equations on the right. So for simplicity, I'm here presenting the version without any symmetry or braiding. And when we interpret this structure in Prof, we obtain precisely the Cauchy-complete trace monoidal categories. Notice that the tightening and sliding axioms, i.e. the structural ones that I had in yellow before, they've disappeared. In some sense, they've been absorbed into the ambient geometry of Prof. And each one of these axioms, which we need to check, and we do so in the paper I talked about, corresponds to one of these green equations that I had before that specify compatibility with tensor. So this framework gives a new external description of trace monoidal categories, and we've used it to prove some small results and conduct a general exploration of the topological nature of tracing in this context. So we spent a decent amount of time trying to generalize the result by Hasegawa and Hajgato that traced star autonomous categories are compact closed to the non-symmetric case. And we made some progress on that front, giving a smaller sufficient condition in which this would hold. In this talk, I left out a lot of details, and I didn't get a chance to talk about our proof methodology of internal string diagrams, which are a super interesting topic in their own right. So please make sure to check out the paper if that sounds interesting to you. Thanks so much for your attention. I expect to be in some of the Q&A sessions, So you can catch me there if you have any questions. Thanks again.